Hello, my name is Nathan Gillet. I'm a research scientist with Environment and Climate Change Canada, and I co-led one of the chapters of the Intergovernmental Panel on Climate Change report on human influence on the climate system. So I'm going to be talking about that report today. But first I want to start with a quick introduction to how I got interested in climate change. So I was studying physics. I was in my first year of a physics degree, and I was interested in the weather. My dad was an environmentalist, so I was starting to hear about climate change back in the 1990s, the early 1990s. And I thought it would be interesting to work in a climate research institute. So I was kind of early days of email and search. Then I typed into Yahoo Climate Research Institute, and a few different places came up. I sent some emails to the heads of these different institutes to see if they would offer me a summer job. And I just got one reply back. It was from someone called Klaus Hasselmann, who was the head of the Max Planck Institute for Meteorology in Hamburg at the time. And he encouraged me to go there and work the next summer. And at that time, it was kind of the early days for climate modeling, for atmosphere ocean modeling. And the scientists there were really putting these models together and just kind of looking to see how they worked, how whether they could reproduce what was really going on in the climate. It was very much kind of early days, might not have been viewed as hard science by the physicists in the department where I was doing my degree. Fast forward 25 years, and things have changed a lot. So if we can go to the first slide, please. If you've been watching the news, you'll have seen that last week, 2 climate modelers were awarded the Nobel Prize in Physics. And one of them, the man you can see on the left there, is Klaus Hasselmann, who was the head of the Max Planck Institute at that time. Really one of the, these two are kind of founding fathers of climate modeling, and also has worked a lot in the attribution of climate change. So really understanding the causes of climate change, which was something that's key in the IPCC assessment that I'm going to talk about today. And I think, the fact that these men awarded the Nobel Prize just reflects the fact that this science is very well established now, and that's also reflected in the IPCC assessment that I'm going to be talking about today. So if I can go to, we'll go to the next slide now. The IPCC assessment is, so the United Nations is the parent body of the IPCC, and it brings out 3 reports. The first report is on the physical climate system, for the climate itself. That's the one that came out this year that you will have seen in the news over the summer. There's also a second report on impacts of climate change and a third report on mitigation of climate change, what we can do to slow climate change. Those reports will be coming out next year. But it's the report on the physical climate system that I'm going to be talking about today. And this report had 234 authors from 65 countries, so very geographically diverse group of authors contributing. And these authors were arranged in chapter teams, and in chapter teams, we developed the assessment of the scientific literature, and then that got distilled down into a summary, which I'll be talking about today. You can see there was 28% women, 72% men, so some way to go on gender parity, but certainly an improvement compared to past reports. As part of this review, more than 14,000 scientific publications were assessed. So it's a huge volume of scientific literature. The process of developing the report took more than 3 years. And these chapters went through multiple rounds of review. We considered, as a team, over 78,000 review comments. And in the final rounds of review, these chapters and the summary were reviewed by governments from around the world. the final step in the preparation of the report, the summary for policymakers. It is approved in a line by line by government representatives from around the world. So, and it's very much a kind of co-development process between the governments and the scientists who write the report. I think it's unique across science. It's a really successful way in which science can inform international policy, in this case, international climate policy. So I'm going to start with some of the key messages from the report, and then I'll dive into the analysis in a bit more depth after that. So these are the key messages. Recent changes in the climate are widespread, rapid, and intensifying, and unprecedented in thousands of years. It's indisputable that human activities are causing climate change. And in the report itself, we wrote that it's unequivocal that humans are warming the climate system. So it's now a statement of fact that humans are warming the climate system. This is very much built on an area of climate science called attribution, which Klaus Hasselmann was kind of the grandfather of. He did the kind of the groundbreaking work to introduce, to develop the field. Okay, and this human-induced climate change has made extreme climate events, including heat waves, heavy rainfall, and droughts, more frequent and more severe. Climate change is already affecting every region on Earth in multiple ways, so it's not just something we see in the global average, we see its effects in every region. And the changes we experience will increase with further warming. Unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees Celsius will be beyond reach. And of course, I think you probably know that 1.5 degrees Celsius is one of the targets set out in the Paris Agreement. So the Paris Agreement was an agreement between countries to limit global warming to well below 2 degrees and pursue efforts to reach 1.5 degrees. So 1.5 degrees in the report, we're not saying it's impossible, but it is hard to reach, and it requires immediate, rapid, and large-scale reductions in greenhouse gas emissions. Across most of the climate system, there's no going back from the changes that we've seen already. So global warming, for example, is irreversible on human timescales. But if we think about the future changes, some of the changes can be slowed, others can be stopped by reducing emissions, by getting emissions to zero. So I'll come back to this later in the talk, but it depends which aspect of the climate we're looking at, whether we can stop the effects of climate change, for example, by stabilizing, at least stop the climate change getting worse, for example, by stabilizing global mean temperatures, or other variables like sea level continue to respond on longer timescales. But the main message here is that the choices we make now in terms of emissions going forward can limit future climate change. So to limit global warming, strong, rapid, and sustained reductions in carbon dioxide, methane, and other greenhouse gas emissions are necessary. And these reductions would not only reduce the consequences of climate change, but they would also improve air quality. So there are these co-benefits of reducing emissions beyond just limiting climate change. Okay, so those were some of the key messages that came out of the whole report, out of this process of distilling down from these 14,000 scientific publications. But now I'll go into a bit more detail on the analysis underlying these conclusions. If we can go to full screen on this graph, that would be good. Okay, so this is the first figure in the summary for policymakers. The headline there, you can see, human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. And that headline is illustrated by the figure over here on the left. If you see the gray line on the figure is showing variations in climate that were reconstructed from tree rings and other so-called paleo indices. So you can see that global average temperature has not been constant. There have been some variations over the last 2,000 years shown on this graph. But if you compare the variations shown by the gray line over the period up to 1850 with the observed temperatures over the period since 1850, you can see that the warming over the last 170 years since 1850 is unprecedented. So the rate of warming is outside anything that we've seen in the last 2,000 years. So the warming is unprecedented in more than 2,000 years. We can also compare with paleo climate observations going further back in time. And the bar on the left shows the warmest multi-century period in more than 100,000 years. This was the so-called mid-Holocene period, about 4,000 to 6,000 years ago. And that temperatures then were, well, the temperatures that we're observing now are now probably above the level that we observed in the mid-Holocene. And prior to that period, prior to the Holocene, was the last ice age. So we are probably now entering a level of warming that is the warmest for more than 100,000 years. So the changes really are unprecedented on a very long time period. Okay, so the left panel, as I say, is showing how global mean temperature has been observed to change. But can we understand what's driving these changes? Well, yes, we can, and that's shown on the panel on the right. So the black, again, is the observed temperature change over the period since 1850. You can compare that with climate model simulations. And in green, these are climate model simulations forced with only natural climate influences. So in particular, variations in solar brightness, and also volcanic aerosols. So large volcanic eruptions put small particles into the upper atmosphere, into the stratosphere, and these cool the climate temporarily. So if you look, for example, in the 1990s, you can see there was a dip that was following Pinatubo, which was the biggest eruption in the last century. So over that period that I was writing those emails to the Max Planck Institute, the climate had cooled a bit following Pinatubo. But if you compare the black observed temperature with the green simulations with natural climate influences, you can see that the observed warming is way outside the range of variations in temperature due to natural influences only. And then if you compare with the brown curve shows simulations with human influence, so with changes in greenhouse gases and other human factors, including aerosols. So the brown is the model mean, so the best estimate of simulated response to human and natural influences. You can see that that matches the observed warming well. So we can only explain the observed warming when we account for human influences, and the warming can't be explained just by natural influence alone. This next slide, and this is the second figure from the summary, goes into that in a bit more detail and shows the different contributions to observed warming. So the headline there, you can see observed warming is driven by emissions from human activities, with greenhouse gas warming partly masked by aerosol cooling. So if you look at the figure on the left, this shows the observed warming over the last decade relative to the late 19th century. And the observed warming, the global average warming, is just over 1 degree. It's about 1.1 degrees Celsius. So that's the observed warming. You can compare that with estimates of the contributions to that warming, and those are shown in, well, let's first look at the middle panel. These are assessed from so-called attribution studies, and as I mentioned already, Klaus Hasselmann kind of is the grandfather of this field of attribution, but it's basically derived by synthesizing information from climate models and from observations to understand how much different forcings, different factors contributed to observed climate changes. So the bar over there on the left is an estimate of the total human influence. And you can see that our assessment of the total human influence is very close to the observed change. So essentially, our best estimate is that all of the observed warming was caused by human influence. But the next, so again, looking at the middle panel, you can see the next bar shows the contribution of well-mixed greenhouse gases. So greenhouse gases have caused more warming than observed, but this warming has been offset by other human drivers, and in particular aerosols, which I'll describe in a bit more detail in a minute. You can see that the contributions from solar and volcanic drivers and from internal variability, so that just means variations internal to the climate system, those are assessed to be small compared to the observed warming. Okay, and if we now turn our attention to the panel on the right, this shows the contributions to observed warming in kind of even more detail, broken down by emissions of individual species, individual greenhouse gases, or aerosols. So if you look at the biggest bar, that shows the contribution of carbon dioxide to the observed warming. And I think it's pretty well known that carbon dioxide is the biggest contributor to observed warming. It's the dominant greenhouse gas. But that said, the contribution of methane, especially when viewed in this way, is actually pretty large compared to the contribution of carbon dioxide. You can see it's assessed to have caused about 0.5 degree of warming. So carbon dioxide and methane are the two biggest warming contributors. If we now turn our attention to the cooling contributions, you can see that the biggest blue bar is labeled sulfur dioxide. So sulfur dioxide is emitted mainly from burning coal, from coal power plants, for example. Sulfur dioxide is a pollutant. It causes acid rain, and it impacts air quality, but it also has an effect on climate. It gets oxidized, turned into sulfate aerosols, and these are small particles that reflect sunlight, and that tends to have a cooling effect on climate. So I'll come back to this, but although that sounds good from a climate perspective, it's very bad from a human health perspective and in terms of its impacts on ecosystems. So it's not something that we kind of want to keep emitting. Okay, so that was showing how, so I was just discussing how contributions to past climate change. What about future climate change, and how are these contributions expected to change in the future? So future emissions cause future warming, with total warming dominated by past and future carbon dioxide emissions. As climate scientists, we kind of study how the climate responds to changes in greenhouse gases and other factors. So for the future, we need to have scenarios, we need to have an idea of how these gases are going to change in the future. And that's what's shown here. So these are different possible futures for how emissions of different greenhouse gases could change. And if you look at the big panel there on the left, panel A, you can see various lines. So if you look at the light blue line, that's so-called SSP 1.9. This is a scenario in which greenhouse gas emissions decline sharply. And this is really the only scenario that gives us a chance of keeping warming to below 1.5 degrees Celsius. You can see that starting right now in the 2020s, emissions are declining sharply, and they are reaching zero emissions in the 2050s. So that is zero net human carbon dioxide emissions. And in fact, if you look beyond that, you can see that the emissions actually go negative in this scenario. And that means that humans are artificially removing carbon dioxide from the atmosphere in this scenario. That could be things like large-scale afforestation, planting trees where there weren't trees before, or actual clear air carbon capture and storage, so removing carbon from the atmosphere. Okay, so that's the lowest emission scenario. You can see there's a range of higher emission scenarios, and the 1.5 is the most fossil fuel intensive scenario, and that is, well, it's a very fossil fuel intensive scenario. Hopefully that's not going to happen now. The estimate of there's no scenario on there that exactly corresponds to kind of current commitments, current climate policy, but it's somewhere between the orange and the light red scenario. So somewhere between SSP2 and SSP3 is kind of current climate policy. So you can see that current policies don't get us close to 1.5 degrees yet. We need more commitments if we're going to limit warming to 1.5 degrees or even 2 degrees. Okay, so that's CO2 on the left. If you look on the right, you can see projected methane emissions, which also decline in the blue mitigation scenarios. So we have to reduce methane too if we're going to limit climate change. Nitrous oxide, that's another greenhouse gas, particularly emitted from agriculture and fertilizer manufacture. And then down at the bottom, you can see changes in sulfur dioxide emissions. So again, I explained that that's a cooling influence on climate, but it has, so sulfur dioxide emissions globally peaked in the 1970s, and they've been declining since then due to clean air legislation and because of the health effects of aerosols and because of their impacts on ecosystems through acid rain. So sulfur dioxide is something that we want to reduce, we should reduce, but we have to kind of take into account that that does increase the warming of the climate somewhat. Okay, this slide just shows how those changes in emissions in the future are expected to change the global average temperature. You can see, as I mentioned already, that light blue SSP 1.9 scenario is the only one that limits global warming to below 1.5 degrees. So if you look at the bar on the left, that's showing the estimated total warming by the end of the century relative to 1850 to 1900. It's just under 1.5 degrees. The other bars in each box show the contributions of different factors. So CO2 is the first bar, carbon dioxide. You can see that that's contributing most of the warming in all the scenarios. Other greenhouse gases make a smaller contribution, and aerosols and land use. Aerosols cause a cooling effect, as I've already mentioned, but that cooling effect is small by the end of the century because we've cleaned up emissions of sulfur dioxide in most of these scenarios. Okay, if you look at the higher emission scenarios, well, the amount of warming goes progressively up, right up to SSP 5, 8.5, where the best estimate is around 4.5 degrees warming by the end of the century relative to pre-industrial. So that's a lot of warming. That's about 4 times the amount of warming that we've observed already, which would have really large, profound impacts. Okay, so far I've been concentrating on the global average change in temperature, but we can also look at the pattern of temperature change, and of course the temperature change has not been uniform everywhere. If you look at the map in the middle at the top, that shows the observed change at 1 degree Celsius of global warming, so that's approximately where we are today. You can see that it's warmed almost everywhere. You can see that the warming has been greater in the Arctic, and that's something that we understand quite well. It's partly due to melting of sea ice and melting of snow, meaning that the ground or the ocean absorbs more sunlight. You can also see that the land has warmed more than the ocean generally, and that's also well understood. So the middle at the top shows the observed change. The top right shows the simulated change from climate models. You can see that the patterns match pretty well between the models and the observations. And one thing to note here is that Canada is one of the areas that's warming faster than the global average. So that led to in a report that we in Environment and Climate Change Canada put out a couple of years ago. We noted that Canada is warming at twice the global rate, and that's projected to continue into the future. So Canada is an area that's warming more quickly than the global average. If you look on the bottom, you can see the projected changes in temperature at these different warming levels. You can see that the temperature changes intensify as the global warming gets larger, increasing to about, increasing right up to that 4 degrees global warming level with, profound, very large changes in temperature of more than 7 degrees in the Arctic and in northern Canada under those high warming levels. So that's temperature. The next figure, this one shows changes in rainfall or changes in, so precipitation is a kind of meteorologist, climatologist word for rainfall and snowfall considered together. So if you look, while it's projected to get warmer everywhere, it's not projected to, so the rainfall change can be either positive or negative depending on where you are. On average, there's an increase in rainfall, and you can see that, for example, here in Canada and in the northern high latitudes, generally we see an increase in rainfall, largest in the Arctic. You can see that also in some parts of the tropics, there's big increases in rainfall. But there's also regions in the subtropics. So if you look at the Mediterranean, for example, where it's projected to get drier, where the amount of rainfall is expected to decrease. Also in parts of Mexico and the southwestern USA, you can see the same thing. And these changes, well, particularly at the higher warming levels, can be pretty big, in excess of 40% increases and decreases. Okay, so far I was just showing how the average temperature and rainfall are projected to change, but we also have to think about changes in extremes if we're interested in impacts. So I live out here in Victoria, British Columbia. We experienced the heat dome in June, and that was really, well, even for someone who studies climate change, it was really quite a shock. We exceeded our previous record high temperatures here by more than 4 degrees. And, it's never 40 degrees here in Victoria. Walking out of the door into 40 degrees temperature was really, really something. And, initial analysis has already shown that this kind of event would have been virtually impossible without human-induced climate change. So we are seeing the effect of human-induced climate change in extremes already. So this figure shows that projected changes in extremes are larger in frequency and intensity with every additional increment of global warming. And I'll zoom in on the top panel first. So for example, if you look at the left, the graph on the left here, you can see that a 1 in 10 year heat wave in the 19th century, so in 1850 to 1900, at the present level of warming, that's now occurring about 3 times as often. So it might be every 3 years instead of once every 10 years. If we go up to 4 degrees global warming level, that 1 in 10 year event is now occurring 9.4 times, so almost every year at a 4 degree warming level. And this is kind of an average over the globe, but it just shows that what was once a rare event is already much more common and is projected to become much more so at these higher global warming levels. This figure shows a similar thing, but for heavy precipitation, heavy rainfall. As the atmosphere warms, it can hold more water vapor, and that means that the heaviest rainfall events are expected to get heavier. And in fact, we're observing that on a global level already. So similarly to the figure that I just showed, a once in 10 year rainfall event, so the heaviest, the day with the most rainfall in 10 years, in 1850 to 1900, that's now about 1.3 times as likely, so about 30% more likely. And then at these higher warming levels, you can see that by 4 degrees of global warming, that's about 3 times more likely. So we are projecting increases in these heavy rainfall events as well. And obviously that can have impacts on flooding and other things that could be important. The last figure here is for droughts. Similarly, so this is just everything so far was for across the globe as a whole, but this one is for just the regions that are projected to dry. But in those drying regions, we do expect an increase in droughts. For example, the 1 in 10 year drought is now almost twice as likely in those regions, and at 4 degrees warming, it would be more than 4 times as likely. Obviously, droughts can have big impacts on agriculture and on water supply, among other things. Okay, so so far I've focused on temperature changes by the end of the century, but now I'll show you a little bit more about how some different climate variables are projected to evolve over the course of the next century. And the first figure here is showing global surface temperature changes relative to 1850 to 1900. So the black shows simulations of past change. I've already shown that those are similar to what we've observed over just over 1 degree of warming to date. But then if you look at the colored lines, that shows different possible futures of how temperature could evolve through the rest of the century. The highest warming level, that's a fossil fuel intensive development scenario where we continue to exploit fossil fuels, coal, and so on. And as I said already, that's getting to in excess of 4 degrees, close to 5 degrees of warming by 2100, which is a really large warming, which would have profound impacts. On the other hand, if we are able to reduce emissions, and if we're able to do so very rapidly and reach net zero in the 2050s, then we would be on the SSP1, so the light blue scenario. And you can see that scenario actually peaks around the mid-century at just above 1.5 degrees and then cools down towards the end of the century. And that cooling actually is linked to the negative emissions in that scenario, where we're actually, in that scenario, sucking carbon dioxide out of the atmosphere. So you can see that there's a kind of a range of projected warming depending on which scenario we follow through the century. And obviously, the scenario that we follow will depend on the policy choices made around the world in the coming decades. Okay, so I'll go to the next slide. This figure shows September Arctic sea ice area. So I haven't talked about sea ice yet, but that's another variable where we've seen the impacts of climate change already. We've seen about a 40% reduction in the Arctic sea ice area in September already. The black line there is showing climate model simulations, but they agree well with observations. And then if you look at the colored lines, you can see how this is projected to change going forward. You can see that it's only in the 2 lowest scenarios, so the 2 blue curves there, the sea ice area continues to decline for the next couple of decades, but then stabilizes, albeit at a pretty low level, well below what we're seeing now. But in all the other scenarios, so even the kind of relatively moderate SSP2-4.5 scenario, the Arctic is practically ice-free in summer by the end of the century. So unless we're able to rapidly decrease emissions, we're going to see ice-free or practically ice-free Arctic by the end of the century. This slide shows changes in ocean surface pH. So this is a measure of the acidity of the oceans. And you've probably heard about ocean acidification. So that's what this slide is showing. Ocean acidification is not actually driven by climate change. It's driven directly by the increase in carbon dioxide in the atmosphere. And as that carbon dioxide gets absorbed by the ocean, it acidifies the ocean. Its pH decreases. So you can see that, and we've already observed a decrease in ocean pH globally that we can link pretty definitely to human activities to the increase in carbon dioxide. But this slide shows also how that's projected to change in the future. You can see that in the SSP 1.9, so that's the scenario, again, where we're actually sucking carbon dioxide out of the atmosphere in the latter half of the century. You can see there is some recovery of ocean surface pH there. Whereas in the other scenarios with increasing emissions, you can see there's an ongoing big decrease in ocean acidification. And ocean pH can have big implications, big impacts on ecosystems, for example, on corals, on shellfish fisheries. So it's a very important variable. Finally, I'll just move on to changes in sea level. I think sea level, again, is kind of one of those pretty well-known impacts of climate change. So as the climate warms, the ocean warms and expands. That's one contribution. Also, the warming climate melts mountain glaciers, and it is melting ice sheets, the Greenland ice sheet, the Antarctic ice sheet, and those contributions, well, there's approximately equal contributions from the melting and from the warming of the seawater. But basically, those are increasing sea level. We've seen already more than 20 centimeters of sea level rise, and this is projected to intensify pretty strongly in the future. And sea level responds very slowly to warming, so it's not something that we can even start to reverse, like the pH I just showed you. Even in the lowest emission scenarios, you can see that the sea level rise by the end of the century is projected to be more than 50 centimeters. The sea level rise, of course, is even substantially higher in the higher emission scenarios. But yeah, just to emphasize that even if we reduce emissions, we can still expect more sea level rise. In the high emission scenario, you can see it's approaching 1 meter by the end of the century in the likely range. But I'll also draw your attention to the dashed line there. So that is what we call a low likelihood, high impact storyline. And so there are processes in ice sheet instabilities, which have been studied, but they're pretty uncertain. So there's a chance, basically what the report is saying, that there is a chance that under these high emissions that the sea level could be as high as shown on that dashed line. It's not the most likely future, but it is possible. And you can see that exceeds 1.5 meters by the end of the century. But the thing about sea level is it doesn't respond kind of instantaneously to the temperature and to the warming. It responds very slowly over with a long lag. So if we look further ahead, which is what's shown in this figure, we can expect much larger sea level rises. So the figure on the right shows the change in sea level in 2300. You can see that even in SSP1, so that second lowest emission scenario, the sea level rise is projected to be 0.5 meters to 3 meters. So that's a pretty big sea level rise if you live somewhere that's close to sea level, thinking of kind of river deltas, places like Bangladesh or the Netherlands, or even here in BC, we have areas that are close to sea level. And then in the higher emission scenario, the sea level rise is much greater, 2 to 7 meters by 2300. And in that kind of low likelihood, high impact storyline, we can't rule out sea level rise greater than 15 meters. So that's a huge amount of sea level rise. And obviously 2300 is quite a long way in the future. But if we think about, you can tell probably I'm from the UK, if we think about cities that are built by close to coastlines like London in the UK, for example, it's been there for 2,000 years. Will it still be there in 300 years? It probably a lot of it not if the sea level is that high. So it sounds like a long time, but it is it's not that long compared to the lifetime of infrastructure in cities, for example, that are built on coastlines around the world. Okay, let's move to the next slide. Okay, this is the last figure that I'll talk about before moving to questions. So this slide shows that every ton of carbon dioxide emissions adds to global warming. And this was really a conclusion that came out of the previous IPCC assessment, that it's really the total amount of carbon dioxide that's emitted that determines the warming. If we're thinking about the warming caused by carbon dioxide, Doesn't matter if you emit it all at once or gradually over a long period, the amount of warming that you end up with is going to be almost the same. And the figure here shows the warming on the y-axis, on the vertical there, compared to the cumulative carbon dioxide emissions since 1850. The black is observed historical warming, and then the colored lines are those scenarios going into the future. You can see that, like I just said, there's approximately a kind of one-to-one relationship between the warming and the cumulative carbon dioxide emissions. And then you can also look at how much emissions we see in these different scenarios going into the future. And yeah, sorry, one more thing on this slide. This relationship means that if you have a particular warming target or threshold, like 1.5 degrees, you can kind of read off the graph and see that a cumulative amount of CO2 emissions that you have to limit yourself to if you don't want to exceed that warming. And for 1.5 degrees, if we look at the light blue scenario, that ends up around 1.5 degrees. And you can see that the cumulative emissions, they're shown in that kind of light blue bar at the bottom there. There's about 500 gigatons of CO2 that we can emit under that scenario from now until 2050. Or in other words, and this is directly in the summary, if we want to limit warming to 1.5 degrees, we have to limit our future carbon dioxide emissions to less than 500 gigatons of CO2. And 500 gigatons of CO2 probably sounds like a lot, but we currently emit about 42 gigatons every year. So that's about 12 years of emissions at the current rate if we want to limit warming to 1.5 degrees. So really what this report shows is that if we want to avoid the worst impacts, the worst future impacts of climate change, then we have to act rapidly. We have to make deep cuts in emissions, and we have to get to absolute zero by the middle, net zero CO2 emissions by the middle of the century. I'll leave it there. Thank you, and I'll come to questions. I'm just opening up the questions. Okay, thanks. So I'll go ahead and read the questions and then go ahead and respond. Okay, I'm going to address, so there's a question. You mentioned challenges in initially creating models for climate change. Are there similar challenges in modeling the snowballing effects of climate change? For example, melting permafrost in Russia, releasing more methane, and its knock-on effects. Well, that's a good question. And as climate modelers, we certainly are preoccupied, and we certainly focus on modeling the important feedback processes in the climate system. And this question asks about one of these feedback processes, which is melting permafrost or thawing permafrost. So permafrost is kind of frozen soils, frozen peats. These contain a lot of carbon. As they thaw, that carbon can get broken down and turned into carbon dioxide and methane. And so, yes, that is something that we model in these climate models. It is expected to amplify climate change, to enhance future climate change. And it is something that is expected to be more important at these higher warming levels. So it is accounted for in the projections included in the IPCC assessment. It amplifies warming at the higher warming levels. And it is certainly still a source of uncertainty, but it is, and it's not that straightforward to model, but it is something that we do model in climate models, and we do account for in the projections. Okay. I'll come to another question here. Is there a way to harness aerosols safely as a way to fast-track cooling effect globally? I think that is a good question. So I think that that comes to this topic of climate engineering or geoengineering. That is touched on in this report. So there have been proposals made, for example, to inject. So as I described, volcanoes cool the climate by putting aerosols into the stratosphere. There have, for example, been proposals made to artificially inject aerosols into the stratosphere to cool the climate. There is research looking at this to see whether it's possible technologically. One thing to say, and which this report says, is that this kind of geoengineering wouldn't, you could probably cool the climate in this way. You couldn't completely cancel out the effects of climate change. You would probably reduce rainfall more. You would reduce rainfall to more than to drier than it was basically in a pre-industrial climate. You would not. You would still have, for example, more warming in the Arctic than in other areas of the globe. So you can't completely cancel out the effects of climate change. The other thing is that if you start doing it, then you've got to do, basically you have to continue doing it for essentially forever, because if you stop doing it, then you would expect a rapid warming back up to the kind of climate that, because where you would be at anyway due to the greenhouse gases. So it may be technologically feasible. There is research looking into it, but there's certainly some disadvantages, and certainly the fact that you kind of have to continue doing it forever is one. Another is that it doesn't combat ocean acidification. Okay, I'll take another question. We've already begun to see extreme weather events as a result of climate change. If no action is taken to slow the effects of climate change, what sorts of additional extreme weather events could Canadians expect to see? Well, the clearest change in extremes is more heat waves, basically. An overall warming and more heat waves in summer months. So certainly we would expect to see more heat waves of the kind that we've seen in BC recently. We would also expect more heavy rainfall events causing urban flooding. And going back to the heat waves again, a warmer atmosphere, a warmer climate causes drying. We've seen that, and it's in this report, evidence that this warming is contributing to an increase in fire weather. So we would expect to see more, basically more fire weather, more fire seasons with a large area burnt, as for example, we've seen in BC in 2017, 2018, and again in this year. So those are a few of the extremes that we would expect to see more of with climate change. And I believe we're out of time now. If I could just confirm whether I should continue or... Okay, I'll take one more question. Sorry, I'm just looking for... Okay, transportation and electricity production are the two biggest contributors to global warming. At the same time, the animal agriculture is responsible for 18% of greenhouse gases, such as methane and nitrous oxide. How come we don't hear more about the impact of livestock production on global warming? I think that's a good question. The IPCC special report on climate change and land use, which came out I believe 2 years ago now, did look at the impacts of agriculture on climate change. And as the question states, agriculture is a big driver, and especially animal agriculture is a big driver of greenhouse gas emissions, particularly methane and nitrous oxide. So I think that as the question, the kind of intention behind the question is correct, that animal agriculture is important. And that special report concluded that moving to a low meat, low animal protein diet would have potential big climate benefits. So I think absolutely that the sentiment behind the question is correct, that reducing the amount of meat, and particularly red meat, would have big climate benefits. So I'll close there. So thanks again for joining this session.